Hi guys, and welcome to the first video on chapter 18. What we're going to talk about today is kind of interesting. We're making kind of a quantum leap forward, and I'm going to show you where the theory comes from, but the proofs are too mathematical to go into that. So don't worry about that. That doesn't even really matter that much. We're going to work with distribution models for p hat and for x bar. Remember, if I use hats or bars, that means from samples. The x means from a sample as well. So we're going to talk about a distribution model for p hat where, in this case, check out sheet 1 here. What I have done in columns A through T, A through T, I have randomly flipped 5 coins in each column. Those are the ones and zeros. And then the 6th row from column A through T is the average of those 5 coin flips, which represents, if 1 represents a head being flipped and 0 represents a tail, then that average represents the number of heads that we saw out of those 5 flips apiece. So let's see how this works here. We've got all of these here. Well, I can still use my cursor here, even if Excel's not going to let me write. This 0.6, 0.6, 0, 0.6, 0.4, etc., out to 0.6 over here. Those are all p hats. Those are sample proportions, because I have samples here. Obviously, it represented in each column A through T. I don't have the whole population of all coin flips available. That doesn't even make sense. That would be a limitless number of coin flips. But I've just got a sample number of coin flips. So we have p hats here, sample proportions from these samples of 5 flips, and we've got 20 of them in all. Now these numbers off to the left here, this 0.0 down to 1, those are for bins, and we're going to check out, with these 20 numbers here, we're going to check out what a histogram of those looks like. And that's what we've got in sheet 7. So in sheet 7 here, off to the left, you've got a nice numerical distribution or breakdown of the distribution of sample proportions of, did we say heads? Yeah, heads of the 5 coin flips. And in this histogram, you've got, in your bins, organized the number of times we saw that particular sample proportion in 5 flips. So that is to say that we saw flips between, in the 0.2 range, 5 times of the 20. In the 0.4 range, 3 times. We saw 0.6 a lot, 8 times. And we saw 0.8, so 4 of 5 heads. We saw that, is that 4 times? It looks like 4 to me. So you've got all 20 samples represented in this histogram, and the shape is, notice, a little bit bell curve-ish. Not entirely the case, but a little bit so. Well, let's talk for a second what we should expect to see in this sort of histogram of sample proportions. We know that for a truly balanced coin, and we're assuming in this case that the quarter, for instance, is truly balanced, the heads and tails are equally likely, we should expect to see a whole lot of sample proportions. Oop, I don't really want to move that, but again, I'll use my cursor here to note what's going on. We should expect to see a whole lot of sample proportions right through here in this area, because the likelihood of getting 1 head is 0.5, right? And the likelihood of a tail is equal to that 0.5 as well. So the histogram looks a little wonky because we only flipped 5 times. Now let's up the ante. Let's go over to sheet 2 here, and let's check out what we have here. So in this case, now I'm still looking at sample proportions, but in columns A through, again, over to T, so that's 20 samples randomly generated here in all. We have 1s and 0s 20 times as opposed to 5. And in row 21, we've got the average number of heads again. So if 1 is a head and 0 is a tail, in the first column, column A, we saw heads 55% of the time, or 11 out of 20 times. We saw in the second sample that we generated here at random, 50% or 10 out of the 20 coin flips were heads, etc., just all the way across. So again, it's these numbers that we see, these summary statistics. They're summarizing these random events that occurred, these coin flips. These summary statistics in row 21 are what we really care about here. Okay, and then again below that, you just have the same bin setup that we had for the random samples of 5 flips instead of 20 flips that we saw earlier. So that doesn't even really matter. It's all about row 21 here. And in sheet 9, we've got that, we've got a summary and a histogram of the sample proportions that we saw. Notice here, compared to sheet 7, which had a whole lot of scatter to it, sheet 9 has a lot more consistency, which makes sense, right? If you flip a coin 20 times, intuitively, you should expect to see numbers around 0.5, that is 50% of the time that you would have heads, versus if you only flip 5 times. And with only 5 flips, the likelihood that something could go wonky, that you would have a sample proportion of heads being 0.2, so just 1 in 5 times, goes up because there are fewer random trials. As these number of random trials increases in our sample, as we go up to 20 random trials in each sample, then we've got more consistency. And you can really see the bell curve shape taking hold here. I'm trying to sort of air draw this with the cursor. You've got much more of a bell shape here. Smartboard's not working with me with the pen today, so just, I think you can visualize that all right. So, the scatter decreased. Now the way obviously that we talk about scatter in terms of the normal bell curve is the standard deviation. What we're trying to build up to, and I'm trying to show you this as opposed to deriving it empirically, because that's outside the realm of this class. What I'm trying to show you is that when you take random samples and you record the sample proportion for each of those samples, you can actually approximate the distribution of those sample proportions with a normal bell curve. Now, let's jump over to Smart Notebook here. So, things we need to talk about here. To be able to use a normal model to summarize a distribution of sample proportions, well, a couple things going on here. We should expect that for all these samples, the mean is going to follow. That is to say, in all, the mean should follow whatever the true proportion of success is for these individual events, for these random events. So the mean should be at p. For instance, we should expect, and when we collect data from 20 coin flips, that p hat, the sample proportions, is close to 0.5, the true proportion of success when we flip a fair and balanced coin to get a head that is. Okay, standard deviation here for this guy, actually, as you might remember, when we were looking at that Excel workbook, as we increased the number of trials in our sample, the variability decreased. So, off to either side, standard deviation is actually going to be square root of PQ over N. That N in the denominator means that all of this that I'm circling here for you now, that's the standard deviation of P hat, of our sample proportion. Well, that N denotes that as the number of trials increases per sample, as we went from 5 flips of the coin to 20, that the standard deviation should drop. That is to say, the variability and the scattering should drop as well. So to the left of P, then, would be the true proportion of success minus the same standard deviation of rad PQ over N. Okay, so what we have here in this bell curve is a normal model that's approximating the distribution of sample proportions. Now that's powerful. Okay, let me stop for a second and explain what we're going from and to. When we've used the normal bell curve in the past to talk about, let's say, likelihood that that one person's height would be like over 6 foot 2 inches, assuming the population of, let's say, men's heights follows a normal bell curve, we were talking about a single random event happening there. Well, this normal model for p hat is talking about a summary of random events happening, right? P hat represents, again, a sample proportion. So I'm not building a bell curve for one random event. I'm talking about a bell curve that summarizes many random events. And we'll see how this comes into play in our next example. Fear not, there is a context for all this madness. So, okay, this is a normal model for p hat. So p hat actually is our variable. That's the thing that changes from one sample to another. In that Excel workbook that I showed you, we had 20 samples in each different sheet, and p hat changed from trial to trial, or collection of 20 trials to collection of 20 trials, I should say. So, expected value for this, just summarizing here to the left what's already in the bell curve. Expected value p hat should be p. That is to say, we should expect a sample proportion for a coin flip to, and if we care about probability of heads, we should expect that to be 0.5, the true probability that we know to be the case for a fair and balanced coin. Standard deviation for p hat is, where did I write that? Right here. It's equal to the square root of p q over n. Okay, so these two things in unboxing, you need to be able to build a bell curve for a sampling distribution for sample proportions. Okay, now conditions that have to be met to be able to use the bell curve to represent sample proportions. First of all, you've got to know that your trials, in this case, the coin flips that I was talking about, need to be drawn randomly. If you're not conducting those events randomly, then this has all gone out the window. We're talking about random events still. 10% condition. If sampling has not occurred with replacement, remember replacement would be, let's say we're talking about a small town in Indiana, and we've got a small group of people, and we want to know the true proportion of people who support Obama over Romney. Well, if I'm not drawing with replacement, we've got, just say, 200 people in the town, and I'm sampling people from the town, the true proportion of people who favor Obama over Romney clearly changes as I take one person out of those 200 people in the town and don't put them back into the pool to be drawn from. So, as long as sampling has not occurred with replacement, then you've got to make sure that each sample we're collecting is no more than 10% of the population of interest. Okay, so that's the second condition. Again, little fuzzy. This stuff is tough to understand initially. We are building up to inference testing, and that's actually what we're doing today, along with confidence intervals. Confidence intervals are powerful as well. First couple of chapters we work with this, it's going to be pretty fuzzy stuff, and I fully expect that. I saw that last year from students as well. A couple weeks in, you guys will really start, this will start to click, and the good thing is that this is going to stick around pretty much the rest of the semester. So yeah, it'll be tough initially, but once you get the gist of it, you guys will flourish with this. Students did last year. Success failure condition, the sample size must be large enough so that at least 10 successes and 10 failures are expected. Reason for that, think back to, well, let me show you. In the Excel workbook. Oh, did I close that? I guess I did. No, I didn't. Okay. In this Excel workbook for p hat, when we only had 5 samples that we were drawing, things got really wonky. Clearly we did not have in each sample, if we're only flipping a coin 5 times, at least 10 heads and at least 10 tails expected. Over here in sheet 9, where we had 20 random flips of a coin, well, if the probability of success of getting a head on any individual flip is 0.5, then yeah, clearly we have 10 expected successes and 10 expected failures, and that takes on more of the normal bell curve shape. So that's why that third condition is what it is. That's to help guarantee that we've got a bell curve shape for sample proportions. All right, enough theory, let's apply this. Suppose that 10% of the population is left-handed. A 200-seat school auditorium has been built with 15 lefty seats, seats that have the built-in desk on the left rather than the right arm of the chair. In a class of 90 students, what's the probability that there will not be enough seats for the left-handed students? Okay, so we want to conceptualize this as we want to think about 90 groups of 90 students, and we want to analyze that proportion of them who are left-handed of the 90. If that proportion is greater than 15 out of 90, 15 over 90, then we've got a problem because we don't have enough lefty seats in this 200-seat school auditorium. All right, so how to analyze this? Well, we're going to start with our conditions. When we want to try to attack a problem where we think we can apply a sampling distribution, a distribution of sample proportions, we need to start by identifying whether or not the conditions have been met. So the three conditions that we just talked about last slide are as follows. And when you attack a problem like this, you need to write that the conditions have been met out. Don't gloss over that. It's it's important both come test and quiz time in my class and on the AP exam. So randomization. Okay. We need to assume, or we can assume rather, we can assume that the 90 students are a random sample of students. Okay, and again you've got, I pulled this problem from the book. I like it, but again you notice that it's not really telling you whether or not randomization is there. To proceed forward with the problem, we have to assume randomization, so we're making note of that now. This bell curve of sample proportions that we talked about last slide hinges on this randomization condition being met. So there's the first thing. Second thing, the 10% condition. We have to meet this condition because, obviously, in this class, we're drawing 90 people from the population of all students that are out there. These people aren't being put back in the population. For instance, you can't have, obviously, 90 students of the exact same person. I could not be the student that we're the student in this group 90 times. It doesn't make sense. So we are not drawing with replacement. So we do need to check the 10% condition. Well, 90 is certainly less than 10% of all students. That is to say that we know that there are more than 900 students that could potentially fill this school auditorium. Think big terms here, just in the world. Okay, so there's the second condition being met. Third condition is that we expect at least 10 successes and at least 10 failures. I'll abbreviate that with S/F condition. Okay, so number of students we have, 90, times the probability of success. Well, if the probability of success is 0.13, because the lefties are the people we care about, then we've got 90 times 0.13, which is equal to, where did I put that? 11.7, which is surely greater than or equal to 10. So we expect to have at least 10 students out of the 90 who are left-handed. Now let's check failures. N times Q would be the expected number of failures. 90 times, instead of 0.13, the complement of that would be 0.87, which is equal to 78.3, which again is greater than or equal to 10, so no sweat there. So the three conditions that we care about to approximate this scenario with a normal distribution of sample proportions has been met. That is a mouthful. Again, I know this is crazy right now. It's kind of fun to work with once you get the hang of it. All right, conditions met. So we want to build a bell curve. I'm going to go to a different color for that, and I got to adjust something here. My VGA cord's messing up. Okay. So bell curve here. This bell curve represents, that's okay, represents the distribution of sample proportions of lefties. So p hat that we care about is equal to proportion of 90 students who, oh, I guess I don't need a lefties over here if I'm defining p hat to include the lefties. P hat proportion of 90 students who are lefties. So there I am defining my variable. P hat's actually my variable of interest. And all of this we could title, again in classic Mr. Shelton fashion, not leaving myself enough room at the top of this. This is a distribution of p hat. Okay, so mean and standard deviation. From last slide we said that the mean of all these sample proportions, that is to say, if we looked at 90 students over and over and over and over and over again, we should expect that each group of 90 students on average, not necessarily every time, but on average, would be 0.13, right? We should expect the number of people in 90 students who are left-handed to be 0.13, which is the population, the proportion of the population, the entire population who is lefties. So 0.13 goes right here. So expected value of p hat we know is 0.13, the true proportion of lefties among the entire population of people. And standard deviation of p hat we need as well. So how much variability do we expect to see from sample to sample? Well, we said that's the square root of pq over n. Plug in p here is 0.13, q is 0.17, n is 90. That's our sample size. And you get 0.035 approximately. So to either side, we have 0.165 and 0.095. Beyond that, we have 0.20 and 0.06 for sample proportions. 1 and then 2 standard deviations out. Okay, so we need to, now maybe this isn't clear. What we're comparing to, let's do this in green. They want to know how likely is it that 15 seats is not enough. So how likely is it that the proportion of 15 over 90 doesn't get the job done? Well, 15 over 90 is 0.167, so our cutoff value is right over here. That's our value of interest. Think in terms of the x value that we use for the normal bell curve. That's the cutoff value. So there's our p hat at 0.167. So we need, well, this is a normal bell curve, so if we're going to find the likelihood that the proportion of lefties be that or greater, that is to say, so that 15 seats wouldn't work, let's use a z-score. So the z-score of p hat, sub p hat, is equal to the value of interest we know is 0.167 minus our expected value p hat of 0.13 all over the standard deviation of 0.035. That comes out to be, where did I put this? 1.06. Does that make sense? Yeah, it does. Okay, so let me scroll down here real quick. So the probability that the sample proportion, the group of 90 students, would have of those 90 more than 16.7% with lefties is equal to the probability that the number of standard deviations out that group of 90 would be is greater than 1.06. Use normal CDF of 1.06 for a lower and 1,000 for an upper, and you should find 0.1446. Okay. We will absolutely look at another problem like this in class. These are weird. They're weird problems. Like I said, with a couple weeks' time, you guys will really get to adjust to these. But right now, initially, I expect kickback. So do what you can with this. Take good notes, and we'll talk about this sort of scenario more in class. Context is not gone with these types of problems. All right, so we're done looking at the first of two things here. I need to check the time. 25 minutes? Okay. I'm going to speed it up a little bit for X bar. Okay, next thing I want to look at, so we've talked about a distribution for sample proportions. Now we need to talk about a distribution for sample means. Here you've got in columns A through T, so it's 20 samples in all, just like we did with proportions. You've got the first two rows are rolls of a die, and that so this A in cell A1, you've got in a random roll of a die result of 5. In cell A2, random roll of a die is 3. And then in the third row, you've got the average, the mean of these samples, these 20 samples of size 2. And then this stuff right in here, that's bins that we're going to use for a histogram. So in sheet 4, check out what's going on. This actually takes on a pretty decent bell curve shape. We've got frequency of sample means between 0, 1, 2, 3, 4, 5, and 6 listed in this histogram. So you should expect that 3.5 would be a common average because the average, whoop, did that again. The average of 1, 2, 3, 4, 5, and 6 is 3.5 right in here. So what are we talking about? We're saying again that for 20 samples where we roll 2 die and take their average, we're seeing often results of 3.5. We saw that frequency. Oh, I guess I made a lot of trials here. I didn't do 20 trials here. I did 100 trials. We saw that about 33 times. No, 32. That's on the cursor. Okay, so we saw results of, with an average from 4 to 5, no, 3.5 to 4.5, 25 times, 19 between 4.5 and 5.5, and then 6 times between 5.5 and 6.5. So the farther you get out from the expected mean for these samples, the less likely that is. Okay, now let's compare that to in sheet, I want sheet 2. Let me scroll up here. Oh, there's nothing to scroll up through. Okay, we've got here in columns A through pretty far out, CV, there are 100 trials. Now instead of just 2 rolls of a die, we're doing 5 rolls of a die, and row 6 is the summary. That's the sample mean that we care about. So we've got 100 sample means in row 6. In sheet 5, notice that compared to sheet 4, when we only rolled the dice 2 times and then took a sample mean, in sheet 5, with 5 rolls of the die, we have a lot less scattering, just like when we were talking about sample proportions. And the frequency that we're seeing results between 3.5 and 4.5 for sample means has gone up considerably. Still 100 trials in all. We're just rolling more dice, which means that low values of an average of 1 are just that much less likely, because think about it, if you've got 5 out of 6 ways to not roll a 1, then to see an average of 1 on, if you've got 1 out of 6 ways to roll a 1 on a die, then to get an average of 1 with 2 rolls would be 1 over 6 times 1 over 6. With 5 rolls of the die, you've now got 1 over 6 times 1 over 6 times 1 over 6 times 1 over 6 times 1 over 6. So it's just that much less likely to see small means here. Okay, done with Excel, because I want to speed this up. Summary of normal model for sample means. Conditions, let's fill that in. We got to fill in the bell curve here. So we should expect that each sample on average is going to follow the population mean. Population mean of a die is going to be 3.5, perfectly between 1 and 6, 2 and 4, 3 and 1 and 5, 2 and 3 and 4. Okay, so we've got a mean value here of mu. We've got standard deviation off to either side of mu plus sigma, the population standard deviation over the square root of n, and mu minus sigma over the square root of n. Okay, so if in this case x bar is our variable of interest, that is the summary statistic from sample to sample that we're building a bell curve for. The expected value of this, expected value of x bar, should be the population mean. That is to say, again, if we take with those 100 samples of size 5 for 5 rolls of the dice, we should expect, in general, to see a lot of, or at least numbers around 3.5, the average number that you would see on a roll of a die. So there's the expected value. Standard deviation of this variable of interest, this summary statistic, this average, is equal to sigma over the square root of n. Sigma is the population standard deviation for a roll of a die in this case. Okay, don't worry too much about this with the exception of the denominator. Denominator, again, notice that as the number of trials goes up per sample, the standard deviation, the variability in x bar drops. Okay, so conditions to be met. First, you got to have randomization again. You got to have random samples, else this logic doesn't work. Independence assumption. You need to make sure that the random samples are mutually independent. That is to say that one roll of a die, getting back to the Excel spreadsheet, doesn't determine the result of another roll of a die. Or if the samples are drawn without replacement, that is to say that we're not taking something or someone from the population and throwing them back in to be sampled again potentially, then we need to check the 10% condition. So this right here hinges upon replacement. If replacement is not happening, then we need to check it, otherwise we don't have to worry about it. And then the large enough sample condition, if the population we're sampling from is unimodal and symmetric, small samples seem okay. If the population we're sampling from is strongly skewed, we'll need larger samples to get an accurate representation of the distribution of sample means. What does that mean? Okay, let me give you an example here real quick. We'll talk this through. So let's say that I want to talk about a distribution of sample means of high school girls' heights. Well, high school girls overall, we should expect to have a unimodal and symmetric distribution of heights. A lot of girls are going to be around the same average height. High or low heights, tall or short kids are going to be a lot less likely, and therefore we would have a two-tailed distribution like the normal bell curve if we built a histogram. Contrast that with if we talk about employee salaries, right? Employee salaries are all over the map, especially here in the United States. We have a huge disparity between what a CEO makes and what sort of the white-collar or blue-collar labor makes. There's a lot of people who make around low middle-class wages, but then CEOs are paid sometimes hundreds of times what those beneath them are paid. So that distribution of the population of employee salaries is not unimodal and symmetric. Therefore, we need to make sure we have larger samples to capture the fact that the employee salaries distribution would be heavily skewed to the, it would have a strong tail to the right. That's what I'm trying to say. All right, so suppose that mean adult weight is 175 pounds with a standard deviation of 25 pounds. An elevator in our building has a weight limit of 10 persons or 2,000 pounds. What's the probability that the 10 people who get on the elevator overload its weight limit? Okay, well, for this, what we really care to find here is if x bar is equal to the, how do I define that? Mean weight of 10 elevator riders, then we want to know, they wanted us to find what's the likelihood that we exceed the 2,000 pound weight limit. We really want to find what's the probability that x bar be over 200, right? Because if there are 10 people and the total weight is 2,000 pounds, then on average, each person would have to be over 200 pounds. So there's X bar defined. Well, we need to talk about our conditions next. Can we approximate this with a normal bell curve? First thing here, randomization. We assume the 10 people on the elevator are a random sample of 10 people. Without that, again, the logic doesn't move forward. Now, that maybe is questionable. Obviously, if you got 10 people getting on an elevator in the Midwest, their weights might be heavier than if you got 10 people getting on an elevator on the West Coast or the East Coast. But we still need to assume randomization here anyway to move forward with the logic. So independence is the next thing we need to check. And for that, the 10 weights should be independent, right? One person's weight doesn't technically affect the next person's weight. Now, again, that may be off a little bit. Potentially you've got a family of 10 people where, yeah, their weights affect each other because they may be genetically linked, they may live under the same household, eat the same food, so independence may not be fair in that case. But again, that's why we're stating these conditions here. We're stating the conditions that have to be there in this sample of 10 people for our result to make sense. Without these conditions, our result really wouldn't make sense. Okay, so because we're not drawing with replacement, we need to check the 10% condition. And yeah, that makes sense that the 10% condition is met because 10 people getting on an elevator is not more than 10% of all the people who could get on an elevator. 10 peeps, not greater than 10% of all people getting on an elevator. All right, last one here, condition 4, to check for this distribution of sample means that we care to build, is the large enough sample condition. Okay, now this is where we think about the population at hand. Are 10 people, are the weights of people going to be unimodal and symmetric? Yeah, we know that they are. We know that if people have a mean adult weight of 175 pounds, in general, people are going to fall around that weight. You're going to have exceptions, both high and low, but intuitively, we should expect the population of people's weights out there to follow more or less a bell curve. It would be kind of, it would have a tail on the right side for sure. Because obviously, you can only drop about 50 pounds or so from 175 and still be healthy, but people weigh a lot more than that in the 175. Okay, so 10%, or the least large enough sample condition, the distribution of people's weights is unimodal / symmetric, so the sample of 10 seems large enough. Okay, conditions are met. Awesome. So, we define the variable, the mean weight of 10 elevator riders. Conditions have been met. Let's go to blue for the bell curve again. So, let's draw that in. Give it a title. This is the distribution of X bar. We already defined X bar. Expected value is the mean that we're going to use for our bell curve here, is equal to 175, what we'd expect one person to weigh. Standard deviation of these sample means of 10 elevator riders, we know is equal to sigma over the square root of n. Well, sigma, people vary in general on an individual basis within 25 pounds of 175 pounds. So 25 over the square root of 10, our sample size. That's equal to 7.91. So let's fill out our distribution here. 175 in the middle. To the right, we've got 182.9. To the left, we've got 167.1. Okay, so again, we need a z-score, because we're talking about a value over here where the sample mean of 10 people would be equal to 200. So z sub x bar, or no, let's do z sub 200, the number that we care about in this case, is equal to 200 minus the mean of this bell curve of 175 over the standard deviation of this bell curve of 7.91, which comes out to be 3.16. So we are quite a few standard deviations from the mean. So the probability, this is going to wrap up the notes, that our sample mean of 10 people would be greater than 200 is equal to the probability that the z-score for those 10 people in their average weight would be greater than 3.16, which is equal to 0.0008. So 0.08%. So very unlikely that you would have 10 people with weights exceeding the tolerance here. That's it. Notes were long. You guys did well. Talk to you next time.